All right, let's jump right in. Today, we're tackling one of the coolest, most fundamental ideas in all of modern AI. We're talking about how computers learn to understand what words actually mean. It's a journey from language to logic, where we literally turn meaning into math. So let me just start with a simple question. How on earth does a computer, a bunch of silicon and code, figure out that the word puppy and the word dog are super related, but that dog and car are basically strangers? Well, the answer is this brilliant concept called text embeddings. And in this explainer, we're going to break down exactly what they are, how they're made, and, most importantly, how you can actually use them. So what is a text embedding? At its heart, it's just a way to translate words into a list of numbers, what we call a vector. But here's the magic. It's not a random list of numbers. This vector acts like a set of coordinates, placing that piece of text onto a giant multidimensional map of meaning. And on this map, things with similar meanings are located right next to each other.
Okay, so how do we actually go about building this incredible map? This is where we get into the core idea of semantic understanding, giving a computer the ability to grasp context, nuance, and all those relationships between words.
It all starts with a function, or what we usually call an embedding model. You feed it any piece of text you want, a single word, a sentence, even a whole book, and it spits out that vector, that list of numbers. That vector is the text's unique address on our map of meaning. You can think of it as a set of coordinates, and the number of coordinates, the number of dimensions, well, that just determines how detailed and nuanced our map can be. So we've got all our text plotted as points on this map, but how do we actually measure the relationship between two of those points? For that, we use a clever tool called cosine similarity. Now, instead of measuring the straight line distance between 2 points, it measures the angle between their vectors. It's basically asking, are these two ideas pointing in the same direction? If you get a score of 1, that's a perfect match. It means the two vectors are pointing in the exact same direction. The meaning is identical. Think of something like the dog is cute and the cute dog. A score of 0 means the vectors are at a 90-degree angle to each other. They're totally unrelated. This is our classic dog and car example. There's just no semantic connection there. And, of course, a score of -1 means the vectors are pointing in completely opposite directions. They represent concepts that are direct antonyms, like hot and cold. This all sounds great, but it brings up a huge question, right? How does the AI model learn where to put these words on the map to begin with? It's not magic, it's actually a really clever training process that's all about contrast. And the technique is called contrastive learning. The name itself gives us a pretty big clue. The model learns by comparing, by contrasting, tons of different pieces of text to figure out what's similar and what's not. Here's basically how it works. You show the model millions of examples. You give it positive pairs like dog and puppy, and you tell it, hey, these two are related, nudge their vectors closer together on the map. Then you show it negative pairs like dog and car and say, nope, these two have nothing to do with each other. Push their vectors far, far apart. The entire training process is just this massive game of adjusting and fine-tuning. The model has one single goal: tweak its internal wiring to maximize the similarity score for things that are related and minimize the score for things that are unrelated. You do this millions and millions of times, and eventually that map of meaning becomes incredibly accurate. All right, now that we've got the theory down, let's get a little more practical, because not all of these meaning maps are created equal. You have to choose your compass, and that means thinking about some really important trade-offs.
One of the first choices you have to make is the number of dimensions, which is really just the size and complexity of your vectors. A small model, say with 384 dimensions, is going to be super fast and take up less storage, but the quality of its map might be a little lower. On the other end, you have a large model, maybe 1536 dimensions, that creates this incredibly rich, nuanced map, but it's slower and needs a lot more storage. For most folks, the sweet spot is right there in the middle, somewhere between 768 and 1024.
And there are a ton of different models out there that can generate these embeddings for you. You've got really powerful proprietary models from companies like OpenAI and Cohere, but you've also got this amazing ecosystem of open source models like sentence transformers that you can run on your own machine for free.
Okay, so this all might be sounding incredibly complex, but I promise you, here comes the absolute best part. Using this technology is actually surprisingly simple. Let's take a look at what it takes to get from this theory to some real code.
And that's it.
Seriously, it's genuinely this straightforward. If you're using an open source library, you just pick a model that's already been trained, you call a single function. In this case, it's model.encode, and you just pass it your text. That's it. The output is your list of vectors, totally ready to go. All that heavy lifting was already done for you.
Of course, just because it's easy to get started doesn't mean you can't go wrong. So let's cover a few essential rules of the road to make sure you're using embeddings effectively and avoiding some of the most common mistakes.
Let's run through 4 crucial best practices. First, and this is a big one, always use the same model to create your embeddings and to search them. Different models create different maps, so their coordinates just aren't comparable. It's like trying to use a map of New York to find your way around Paris. Other things, like normalizing your vectors and processing text in batches, will make your whole system way more efficient. And finally, caching your embeddings so you don't have to recalculate them over and over is a huge time saver.
Okay, here's a super common problem you'll run into. Most models have a limit on how much text they can handle at once. So what do you do if you have a really long document? Well, a great solution is to chunk it. You just break the text into smaller, overlapping pieces, create an embedding for each little piece, and then average all those vectors together to get one single representation for the whole document. Another big one is domain mismatch. A model that was trained on the entire internet is probably great for general stuff, but it's not going to understand the specific jargon and nuance of, say, legal contracts or medical research. The solution? Use a model that was specifically trained on that subject matter. There are fantastic specialized models out there for pretty much every field you can imagine.
So, after all that, what's the big takeaway? If you remember just one thing from this, make it this. Embeddings are the absolute foundation of modern semantic search, of recommendation engines, of so much of what we call AI today. They are the engine that finally lets us turn that fuzzy human concept of meaning into cold, hard, and incredibly useful math. And that brings us to the end. We've seen how this incredible map of meaning is drawn, how it's measured, and how we can use it. So the final question really is for you. Now that you know how the map is made, what new concepts are you gonna chart? Thanks for tuning in.